Hello everyone, in this video I'm going to show you how to find the domain of some functions. So let's just jump right into it. So when you're trying to find the domain of a function, you're trying to figure out what real numbers can you input into the function so that when those real numbers are evaluated by the function, you get out another real number. So that function will spit out another real number. And so there's two times where that won't happen. When you have, and those are called two domain restrictions. When you have a variable in the denominator, you have to make sure that the denominator is not equal to 0. Because in that case, if we were to input a number into a function that makes the denominator 0, that's where the function's undefined, so you won't get out a real number. And number 2 is if we have a number less than 0 underneath an even root, right? Because if you were to input a number that made the expression underneath an even root negative, you would get an imaginary number, so that won't give you another real number. So in that case, you have to make sure that the inside here, what's underneath the radical symbol, which is called the radicand, is greater than or equal to 0. Now, if you don't have either one of these two cases, then your domain is just all real numbers. So let's take a look at some examples. So here we have a function where we can clearly see we have variables in the denominator. Again, when that happens, we have to make sure the denominator is not 0. So I'm going to write my denominator and make sure it's not 0. And that's how I write it. And then I just go about solving for x. So I have a quadratic. So I'll write x here in my two binomials, and plus 3 plus 2, because I know 3 times 2 is 6, and 3 plus 2 is 5. And then each one of those binomials can't be 0, so x plus 3 can't be 0, or x plus 2 can't be 0. So x can't be negative 3, x can't be negative 2. So I like to put the numbers on a number line and draw this out. So I have negative 3, and I can't have negative 3, and I have negative 2, and I can't have negative 2 as part of my domain either. But I can have all these numbers in between negative 3 and negative 2, and all these numbers over to the right of negative 2. So looking at my number line from reading left to right, where I shaded, I'm going from negative infinity to negative 3. Infinities always have parentheses. I'll denote that I'm not including negative 3 in my integral notation using parentheses. Union, the numbers in here in between negative 3 and negative 2, again, we're not including negative 3 and negative 2. Union, negative 2 to infinity. So negative 3 and negative 2 are not part of our domain because that's where the denominator is 0. So it would be undefined there. Okay, so here we have another function where we have a variable in the denominator. So again, that can't be equal to 0. And I see here that no matter what number I put in here, I'm going to square it and add 1. It will never be 0. And I can also tell because when I try to solve for this quadratic, I'm going to get imaginary solutions. So I can't solve for it in the real number system. So it's just all real numbers. No matter, our domain is all real numbers. No matter what number we put into here, it'll never make the denominator 0. So there's nothing we have to watch out for. Okay, here I have a quadratic underneath an even root. So an even root, we have to make sure that whatever's under there is greater than or equal to 0. And so I am going to factor this, x plus 3, and then x minus 2, because a positive 3 times a negative 2 is negative 6, and 3 minus 2 is 1. Now I need to find my boundary values. So I need to find where each one of these factors are equal to 0. So I have -3 and 2. So this is where my expression is equal to 0. Now my boundary values, they create intervals. And within those intervals, I'm going to find some test values. I'm going to choose some numbers to test. So I'm going to replace these numbers in here, place these numbers in here, and see if it's true. See where that is true. So I'm going to replace x with 4 to get 16 minus 4 minus 6. And I can see clearly that f6 is greater than or equal to 0. And that's true. So all these numbers are good. Everything over here. And when I replace x with a 0, to see if that is true, I get -6 is greater than or equal to 0, which is clearly false. And so these numbers aren't going to work. And then I'm going to test 3. 4 squared plus 3 minus 6. To get 9 plus 3 minus 6. Well, minus 6 is greater than or equal to 0. And I can clearly see 6 is greater than or equal to 0. That's true. So these numbers are good too. So this is my answer drawn out. Now in interval notation, if I read the number line left to right where I shaded, then I'm going to go from negative infinity to -3. And I'm going to include -3 union to including 2 to infinity. And I denote that I'm including 2 with a bracket. And I can write it down here, or I'll write the answer up here so you can see it better. So the answer is -infinity to -3 with the bracket, because I'm including the -3. That's how I denote that I'm including the number in interval notation. To infinity. So we just drew a picture, and I read the graph left to right where I shaded, and that is our answer. Okay. Now I have this function, and I have an even root and a variable in the denominator. And when that happens, we have to look for both, watch out for both, and find the overlap, find where those intersect, and that's our answer. So I have first one, x minus 3 is greater than or equal to 0, because that's a even root. So I have to make sure the expression underneath that even root, which is called a radicand, is greater than or equal to 0. So x has to be greater than or equal to 3. And then I have to make sure that the denominator is not 0. So x can't be -2. So with the first one, if I draw the first one, x can be greater than or equal to 3. All of this. And this one, x can't be 2, but it can be everything else. And then your answer is where you shaded twice, which is right here. So reading that from left to right, where I shaded twice, it's 3 to infinity. So we have 2 restrictions, and we see those, put those both down on a number line, and where you shaded twice, or the overlap or the intersection, is your answer. And here we have the same thing again. In even roots, we have to make sure the radicand is greater than or equal to 0. So x has to be greater than or equal to -3. And 1 minus x can't be 0. We have a variable in the denominator, and so the denominator can't be 0. So x can't be 1. So x is greater than or equal to 3. So we're putting both of these on the number line. So we have this, and x can't be 1. X can't be 1 here, but it can be all of this. And where do we shade twice? In here and in here. So reading the graph left to right, where we shaded twice from negative 3, including negative 3, to 1, not including 1, union 1, not including 1, comma, infinity. So again, when you have two of the restrictions in this way, you have to work both of them. I like to put them down, draw them on the number line, and then where the overlap is, where the intersection is, or where you shade it twice, that's your answer. And so I read from left to right where I shaded twice. And so I shaded twice from here to here, and then 1 again to here. And we're not including the 1, that's not where we shaded twice. Okay, in this last problem, we do not have any even roots, and we do not have any variables in the denominator. So I don't have to worry about anything. My domain is all real numbers. No matter what number I input in here, I will get out another real number. Okay, well that is all I have. So again, the domain is you're trying to figure out what real numbers can you input to a function that will hand you another real number. And so with these two domain restrictions, it can't happen if there are variables in the denominator. We have to make sure that the denominator is not 0. So it can't happen if those numbers make the denominator 0. And it can't happen if the numbers you input to a function make the expression underneath the root a 0. So we have to make sure that the inside or the radicand is greater than or equal to 0. If you don't have any of these two cases, it's all real numbers. So here's one where you have to be careful. The denominator could be 0 at -3 or -2. I put that on the number line, and then just read where I shaded left to right. And then we had one here where the expression underneath the root, there was an expression underneath an even root, so we have to make sure that's greater than or equal to 0. And so we found those numbers that make the expression greater than or equal to 0, and anything that doesn't, we throw it out. And this was our answer. And here are some more. And so that's it. I really hope that helped. Please feel free to check out my other videos. I have many other videos over many other topics. And that's all I have for today, guys. And I'll see you on the next video. Thanks, guys. Bye.